Hello and welcome back. This is our pre-lab lecture for week 5. And despite the fact that we will be in lab, this is an activity. So this will be 44A. And this covers sections 4.8 through 4.10 in McMurray and activity 44A in the lab manual. And you should read before and after watching the lecture. So, picking up where we left off in the activity. Oh, hang on one second. There we go. It didn't want to scroll for a second. Okay. So, pardon me, picking up where we off on the activity, we learned how to make Lewis structures. And now we're going to determine what the correct shape is. So, the shape of a molecule starts with acknowledging that bonds are made of electrons, which are negatively charged. And since like charges will repel each other, the bonds about the central atom are going to be as far apart as possible. They're all pushing away on each other as much as possible. And so this is called um, VSEPR. Some people pronounce it Vesper, even though that's not correct, but that's okay. It stands for valence shell, electron pair, repulsion. Okay. And so let's go over a definition that we're going to use throughout this lab, and that is a charge cloud. So a charge cloud, that is just a region of space that contains electrons. So any region of space containing electrons. So this could be a bond or a lone pair. Okay, so since we're just describing a region of space, it doesn't matter how many bonds there are, whether it's a double bond or a triple bond. Every single one of these is one charge cloud. Okay, every single one of those. So just to reiterate, um, we said it before that since it does describe a region of space and does not describe the number of electrons. An example is a triple bond um, contains 6 electrons, but is only one charge cloud. Can't emphasize that enough. So let's look at some Lewis structures, and let's look at 4 of them, and we'll see how many charge clouds. So first one will be CH4. So I encourage you to pause and determine the Lewis structure for yourself. But that's going to be carbon in the middle with 4 hydrogens around it. And that is 4 charge clouds. Okay, it's 4 single bonds. So another one is NH3. We've got our lone pair there and 3 hydrogens. This is also for charged clouds. We have 1 lone pair and then 3 single bonds. So let's look also at H2O. Still 4 charged clouds. Sorry, my handwriting got a little messy there. And then let's look at one with a multiple bond that I believe we saw in our activity. That one is 3 charged clouds because that double bond counts as 1. Now let's look at bond angle. So the bond angle refers to the angle between the bonds, of course, but it's dictated by the number of charged clouds. Okay, so if we have 4 charged clouds, our approximate bond angle is 109.5 degrees. Okay, sometimes it's more, sometimes it's less, but those 3 molecules we drew above all have approximately 109.5 degrees between their bonds with respect to the central atom. Now I realize that on paper like this, it looks like we're doing 90 degrees, but this is in 3 dimensions. We can only do so much on paper. There is a way um, to draw it, not draw it in 3 dimensions, but make it represent 3 dimensions, but we're not going over that in this class. So if I have 3 charged clouds, my approximate bond angle is going to be 120 degrees. Okay, and just like we saw on the previous page, this guy has 3 charged clouds, so its bond angle is 120 degrees. Another molecule that we saw in our activity is NO2, and we of course will put that in brackets because it has a minus charge. And those are also 120 degrees away from each other. Then we only really have one option for 2 charged clouds, and that's 180 degrees. And so an example of that would be CO2, 2 charged clouds about the central atom. Okay, so let's tie it all together and talk about molecular geometry. Okay, so molecular geometry is the description of the shape of the molecule. Instead of just writing out the angles, we're just going to give it all a name. So it's according to the number of bonds and the bond angle. And there's a lovely table on table 4.3 on page 118 of McMurray that will show you all the different options for shapes based on the number of charged clouds and how many of those charged clouds are actually bonds. So that table we're going to use quite a bit in our lab this week. So let's look at an example of SO2 versus SO3. So SO2 has three charge clouds. One of them's a lone pair. So it's got a 120-degree angle. So three charge clouds, but it only has two bonding charge clouds. So this is called bent. Okay, please do refer to that table as we go through this. So we also have SO3. Okay, and so that also has three charge clouds, but all three of those are bonding. And so this would be called trigonal planar, a flat triangle. Okay. So this next concept is something we alluded to last week, but we didn't go very deep into, and that is polarity and electronegativity. So we mentioned before that if two atoms are very different, then they will share their electrons unequally. Well, this is the difference that we're talking about, and that difference is electronegativity. Okay, so electronegativity is a measure of how hard an atom pulls on the electrons in a bond. Okay, so I'd like you to see figure 4.7 on page 123 of McMurray, and you can see that each element has its own electronegativity value, and that there are trends based on the placements on the periodic table. So notice that fluorine has the greatest electronegativity value, and that the farther an element away is from fluorine, um, the less electronegative it is. Okay, so when two atoms with different enough electronegativities, if they are different enough and they're covalently bonded, then they will share their electrons unequally. Okay, so the electrons in the bond will go towards the more electronegative atom. Okay, and what happens then is you get partial charges. You know, if one atom entirely steals an electron, then it becomes negatively charged. But if it just partially steals the electron, if it hangs on to the electron most of the time, but not all the time, that would be a partial charge. And so what that forms is called a dipole. Okay, so let's look at some examples. Um, Now I'm not drawing a whole molecule. I'm just drawing the bond. Okay, so that's why there's no lone pairs. Um, Carbon has an electronegativity value of 2.5, and oxygen has an electronegativity value of 3.5. And so I am going to say slightly positive and slightly negative on each side of this molecule. So the slightly positive side is the least electronegative side. Now this looks like an S. This is a Greek delta, but I like to think of it as an S standing for slightly. Let's look at another example. Is we have an O and an H bond. H has an electronegativity value of 2.1, so it's got more of a partial charge. We could say this bond is more polar. Okay. Okay. Polar bonds have their electrons unequally distributed. So the final thing to look at is overall polarity. So you can have, we're looking at individual bonds. We looked at individual bonds just now, but overall polarity has to do with polar bond placement. Polar bond placement within a molecule. So it depends upon bond angles. So for example, a molecule with symmetrical polar bonds would have no overall polarity. So let's look at some polar molecules and some molecules with polar bonds but are nonpolar overall. So let's look at H2O and HCN. So I have my bent shape with H2O. And so these hydrogens are slightly positive, and this oxygen is slightly negative. So I could draw this overall polarity with an arrow, with a dipole arrow. That just says the overall dipole goes towards that negative side. Okay, so HCN is a linear molecule, and hydrogen is the least electronegative, so it's slightly positive on that side. Nitrogen is the most electronegative, it's slightly negative. And so if I want to draw that with a dipole arrow, I would just have that pointing towards the nitrogen, just like that. Now let's look at some examples of nonpolar molecules. So CO2, okay, it's got two slightly negative areas and slightly positive in the middle, but the dipoles cancel each other out. So you have no overall polarity. Okay, same thing with CCl4. All of these chlorines are electronegative. So you have carbon in the middle as slightly positive, and then all of these are slightly negative. And we can't forget our lone pairs. Okay. So, but all of these negative, slightly negative charges are pulling in equal and opposite directions. So, in total, it's a nonpolar molecule. There is no dipole. Okay, this concludes the pre-lab lecture for activity 44A. Forgive the confusion on that. I hope you enjoyed this and thank you for your attention.